Somewhere out there, a dying star collapses into a point smaller than an atom. Everything it ever was gets crushed into a spot where the rules of physics stop working. And here is the strange part. When that black hole finally disappears, the universe seems to forget it ever existed. That should be impossible. Every law we trust says the universe keeps a perfect memory of everything. Every atom, every moment. Nothing gets erased. Yet a black hole appears to break that promise. Today, we chase the deepest puzzle in physics. We will fall past a one-way door. We will watch a black hole glow and slowly die. We will find a wall of fire, tiny wormholes, and a clue that reality itself might be made of information. If cosmic mysteries pull you in, follow along and subscribe. Take a breath. We begin. Burn a page from a book. Watch the smoke curl up and the ash drift down. The words look gone forever. But physics whispers something strange back at you. Those words still exist. Every letter, every loop of ink got scrambled into the heat, the light, and the tiny bits of soot floating in the air. The information didn't vanish. It just got messy. And if you had a perfect enough machine to track every single particle in that smoke, you could, in theory, unscramble it and read the page again. This is one of the deepest promises in all of science. The universe keeps a perfect memory. Nothing ever gets fully erased. Physicists call this idea the conservation of information. It sounds fancy, but the meaning is simple. The present holds a complete record of the past. Every moment carries forward everything that came before it, just rearranged. Think about a giant pool table with a billion balls bouncing around. If you filmed them and played it backward, the motion would still make sense. Every collision would still follow the rules. You could always trace where each ball had been. The universe works the same way, down at the level of atoms. Here is where it gets almost unbelievable. Say you drop a glass and it shatters into 1,000 pieces. Feels permanent, right? But nothing about physics actually forbids those pieces from leaping back together. The tiny motions of every shard, every speck of dust, still secretly remember the shape of the glass. The reason it never rebuilds itself is only about odds, not about the memory being lost. And the odds are wild. For a single shattered glass, the chance of it reassembling by accident is smaller than 1 in a number with more zeros than there are atoms in your whole body. So it never happens. But the memory is still there. Scientists trust this rule so completely that they build entire theories on top of it. It's baked into the math that describes light, heat, motion, and the behavior of every particle we've ever measured. When you push a swing, when a star explodes, when your phone lights up, the same quiet law holds. The record survives. Why does this matter to you? Because it means the universe is honest. The past is real and locked in place. If you had godlike vision, you could look at any drop of water today and read the entire history of the ocean it came from. Nothing gets faked, nothing gets deleted. That's a comforting thought. A cosmos that never forgets. A reality where truth can always, in principle, be recovered. Scientists were so sure of this that for a long time nobody even questioned it. It felt as solid as the ground under your feet. The memory of the universe was safe. Then someone asked a simple question. What if you took that shattered glass, that burned page, that record of everything, and threw it somewhere the rules might break? What if you threw it into the darkest, hungriest object in the sky? Somewhere out in space, there are traps so powerful that light itself gets swallowed whole. And a strange thought started to form in the minds of a few physicists. Maybe, just maybe, the perfect memory of the universe had one terrifying blind spot. To see it, we first have to understand something even more basic. If the universe truly remembers everything, then it should be able to do something that sounds like magic. Imagine you had a camera that could see every atom in existence at the same instant. Every particle, its exact spot, its exact speed, all frozen in one snapshot. With that single picture, and the laws of physics. You could do something godlike. You could rewind the entire universe. This is the wild power hiding inside that perfect memory. If nothing gets erased, then the present moment contains the seeds of the whole past. Run the equations backward and the film plays in reverse. Broken things reassemble. Cold coffee grows warm again. The dead star pulls itself back together and ignites. A French thinker named Pierre-Simon Laplace dreamed this up more than 200 years ago. He imagined a mind so vast it knew the position and motion of every particle in the cosmos. To that mind, he said, the future and the past would both lie open like a book. Nothing would be uncertain. Everything would be readable, forward or back. We call this idea determinism. It means the universe runs like the most perfect clock ever built. Wind it up, and every tick that follows was already set. Not because some fate decides it, but because each moment flows directly out of the one before, obeying rules that never bend. Picture a movie on your phone. You can scrub the little bar forward to see what happens next. You can drag it backward to watch the earlier parts again. The film holds every frame, start to finish. Reality, at its deepest level, behaves like that reel. Every frame is saved. Every frame connects. Now, real life throws in a twist. We can't actually rewind the world because we can never gather that perfect snapshot. There's simply too much to track. The number of particles in just one cup of water is larger than the number of stars in 1,000 galaxies. No machine could ever catch them all at once. So in practice, time feels like a one-way street. Eggs scramble but never unscramble. You grow older, never younger. The mess only ever gets messier. But that's a limit on us, on our tools and our patience. It is not a limit on the universe itself. Deep down in the math, the past stays perfectly recorded. The rewind button exists. We just can't press it. This gives scientists something priceless. It means the laws of physics are trustworthy in both directions. Whatever happens can be traced backward to its cause. Cause leads to effect, and effect points cleanly back to cause. The whole chain stays unbroken. Every experiment ever done agreed. Smash two particles together in a giant machine, study the wreckage, and you can always work out what went in. The books always balance. The memory always survives, all the way down. For a century, physicists carried this belief like a treasure. The universe could always be rewound, at least on paper. The past was never truly lost. It was the bedrock everything else stood on. Then they found one object in the sky that seemed to spit in the face of all of it. An object that eats everything and gives nothing back. A place where the rewind button might snap clean off. To understand the threat, you need to meet the monster itself. You need to understand why, not even light, the fastest thing in existence, can climb out of its grip. Throw a ball straight up. It slows, stops, and falls back into your hand. Throw it harder, and it climbs higher before it drops. Now imagine throwing it so hard it never comes back down at all. It just keeps going, out past the clouds, past the sky, into space. That magic speed has a name: escape velocity. It's how fast you must move to break free of something's gravity forever. On Earth, escape velocity is about 25,000 miles per hour. That's why rockets need so much fire and fury to leave. They have to hit that speed or they fall right back. On the moon, gravity is weaker, so the number drops. You could escape the moon at a fraction of that. On a giant planet like Jupiter, you'd need to go far faster. See the pattern? The more mass an object has, and the more tightly it's packed, the harder its gravity pulls, and the higher the speed you need to flee. Squeeze something small and heavy, and its grip becomes fierce. Now play a dangerous game. Take a star, something with more mass than our sun, and start crushing it down. Smaller, denser, tighter. As it shrinks, its gravity at the surface grows stronger and stronger. The escape velocity climbs. 10,000 miles per hour. 1,000,000. 100 million. Faster and faster you'd have to move to get away. Keep squeezing. At some point, You cross a terrifying line. The escape velocity reaches the speed of light itself, around 670 million miles per hour, the fastest speed anything in the universe is allowed to travel. And that's the trap. Light is the champion. Nothing beats it. Nothing ties it. So, if you need to go faster than light to escape, and going faster than light is impossible, then the answer is brutal and simple. Nothing escapes. Ever. You've just built a black hole. It is the ultimate prison. Gravity so strong that light, the quickest messenger in existence, gets caught trying to leave. And if light can't get out, then nothing can. No signal, no sound, no cry for help. Whatever crosses the line is gone from the rest of the universe forever. Here is a fact that stops people cold. A black hole with the mass of our sun would be small enough to fit inside a city, just a few miles across, crush our entire sun down to the size of a town, and its gravity would swallow light whole. All that raging power packed into something you could drive across in minutes. Even stranger, black holes are almost invisible. They give off no light of their own because light can't leave. We find them by watching how they yank on nearby stars, or how they shred gas into blazing rings before it plunges in. The black hole itself stays perfectly dark, a hole cut out of the night. For a long time, scientists thought that was the whole story. A one-way pit. Stuff falls in, nothing comes out. End of tale. Simple and clean. But that simple story is exactly where the whole nightmare begins. Because if everything that falls in is gone for good, then the memory of the universe has a leak, a place where the record could be lost. To find that leak, we have to walk right up to the edge of the trap. We have to stand at the invisible line where escape becomes impossible and see what waits there. Every black hole is wrapped in an invisible line. You can't see it, touch it, or feel it. There's no wall, no fence, no warning sign, but cross it, and your fate is sealed forever. This line is the event horizon. It marks the exact spot where escape velocity finally beats the speed of light. Outside it, with enough power, you could still claw your way back to freedom. Inside it, no power in the universe is enough. It is a one-way door. The wildest part is how gentle the crossing feels. If a giant black hole were floating near you, you could drift across its event horizon and notice nothing at all. No jolt, no flash, no sound. One moment you're outside, able to leave. The next moment you're inside, trapped forever, and your own eyes would tell you nothing changed. Think of a canoe drifting down a slow river toward a waterfall. Far upstream, the water is calm, and you can paddle back anytime you like. But there's a point where the current becomes too strong to fight. Past that line, no matter how hard you paddle, the falls will take you. And the scary thing is, the water at that exact line looks just as calm as the water before it. You wouldn't feel the moment you lost the fight. The event horizon is that line made of gravity instead of water. Why is it called an event horizon? Because it's a horizon for events. Anything that happens inside it can never send news to the outside. Imagine your friend jumps in while you watch from a safe distance. From your view, something bizarre happens. As your friend falls toward the horizon, they seem to slow down. Their motion crawls. Their light stretches and dims and turns red. They freeze, fading, right at the edge, hanging there almost forever. That's because near a black hole, gravity warps time itself. The stronger the gravity, the slower time flows. Right at the horizon, from your outside view, time nearly stops. So you never actually see your friend cross. You see a frozen, reddening ghost, growing dimmer until it fades from sight entirely. But from your friend's own view, nothing weird happens at all. They fall right through the horizon in a normal amount of time. No pause, no freeze. Two people, watching the same event, seeing two totally different stories. Both of them correct. Hold on to that idea. It becomes very important later. The size of the door depends on the black hole's mass. A small one might have a horizon just a mile or two wide, but the giants lurking in the centers of galaxies are monsters. The one at the heart of our own galaxy has an event horizon wider than the distance from the Sun to the planet Mercury, and some are far larger still, with doors so wide that light would take days to cross them. Once you're through that door, the outside world can still be seen. You can look back up and watch the universe carry on, but you can never send a single message back. You can never return. The door only opens one way, and it opened for the last time the instant you crossed. So now you're inside. The stars above you, unreachable, and ahead of you, at the very center, waits something worse than the door, a destination where the falling ends and the real horror begins. But before you reach it, the trap has one more cruel trick to play on your body. Falling into a black hole would not be a peaceful trip. Long before you reach the center, the trap would do something horrifying to your body, and it comes down to a simple, everyday force behaving in an extreme way. Gravity pulls harder the closer you get. You know this already. Stand up, and your feet are a tiny bit closer to the center of the earth than your head, so they feel a tiny bit more pull. The difference is so small, you never notice it. Your whole life, head and feet, fall together. Near a black hole, that small difference explodes into a nightmare. Say you fall in feet first. As you plunge closer, your feet are nearer to the center than your head. And because gravity ramps up so violently here, your feet get pulled much, much harder than your head. So the black hole starts stretching you. Your feet race ahead, your head lags behind. You get pulled longer and thinner, like taffy at a candy shop being drawn out into a strand. Scientists gave this a goofy name for a gruesome thing: spaghettification. You'd be stretched into a long, thin noodle of what used to be a person. It gets worse. While gravity stretches you head to toe, it also squeezes you side to side. Picture the black hole below you like a drain. All the falling matter, including you, is being funneled toward a single point. So your shoulders get pushed inward while your body gets pulled longer. You'd be stretched and crushed at the same time. Thinner than a thread, longer than a building. The force behind this has a name: tidal force. It's the same force that makes the ocean tides rise and fall, caused by the moon pulling harder on the near side of Earth than the far side. On Earth, it's gentle enough to just nudge the seas. Near a black hole, that same effect becomes a weapon that can tear atoms apart. Here's a strange twist. The size of the black hole changes everything. For a small black hole, the tidal force is savage even before you reach the horizon. You'd be shredded into spaghetti while still outside the door. But for a truly giant black hole, the pull is so spread out that you could sail across the horizon completely intact, feeling nothing, and only get stretched much later, deep inside. Bigger monsters give you a longer, calmer ride before the horror kicks in. How strong does it finally get? As you near the center, the stretching force grows without limit. It climbs past what holds your bones together, past what holds your cells together, past what holds your molecules together. Then it rips apart the atoms themselves. You would be pulled into a single strand of particles, one after another, falling in a line toward the center, and no scream would escape. Remember, you're already past the event horizon. The universe outside would never hear a sound, never see a flash. Your entire violent end would happen in total silence, hidden behind the one-way door. The truly unsettling thought is what you'd be falling toward. All that stretching, all that crushing, is aiming you at one specific place. A place where our understanding of everything falls apart. The center of the black hole holds something that even the smartest physicists cannot describe, because at the very heart of the trap sits a point where the math itself gives up, a spot where every equation we trust simply screams a meaningless answer and stops. What lives there might be the strangest thing in all of science. Keep falling, past the door, past the stretching, all the way down. At the very center of every black hole, our map of reality runs out of ink. The roads just stop. What waits there is a place scientists both fear and can't explain. They call it the singularity. Here's the problem in plain terms. Our best theory of gravity, built by Albert Einstein, is a masterpiece. It predicts how planets orbit, how light bends, how time slows. It has passed every test we've ever thrown at it. But when we point it at the center of a black hole, it breaks. The equations say all the mass of the black hole gets crushed into a single point, a point with zero size. Take the mass of a dead star, more than our whole sun, and pack it into something smaller than a grain of sand, smaller than an atom, smaller than anything, until it has no size at all. When you do that math, the numbers blow up. The density becomes infinite. The gravity becomes infinite. The curving of space becomes infinite. And infinity, in physics, is usually a giant red flag waving in your face. It's the universe's way of saying you've asked a question your theory cannot answer. Think about dividing a number by 0 on a calculator. Try it. The screen shows an error. The machine isn't being lazy. The question simply has no sensible answer. A singularity is the universe flashing that same error message. Our finest theory of gravity hits a wall and displays nonsense. So, what's really there? The honest answer is that nobody knows. This is one of the biggest unsolved mysteries in all of science. The singularity might be a true point of infinite density, or infinity might be a sign that Einstein's theory, brilliant as it is missing something at the very smallest scales. Most physicists believe the second thing. They think that down at this impossibly tiny size, a different set of rules must take over. The rules of the very small. The strange, fuzzy laws of quantum physics that govern atoms and particles. Somewhere in there, gravity and the quantum world should meet and give a sensible answer. The trouble is, we don't yet have the theory that combines them. Finding it is one of the great goals of modern science. There's another mind-bending detail. Once you cross the event horizon, the singularity isn't a place off to the side that you could steer around. Falling toward it becomes as unavoidable as tomorrow. Inside a black hole, gravity twists space and time so severely that the center lies in your future. Every direction you could possibly move leads there. You couldn't avoid it any more than you can avoid getting older. The singularity is simply what comes next. So picture the full journey now. A one-way door you drift through without a sound, a stretching that pulls you into a thread, and a final destination that even our greatest minds cannot describe, waiting in your unavoidable future. For decades, this painted a grim picture of black holes. They looked like perfect destroyers. Everything that fell in got crushed into a mystery point and vanished from the universe. Whatever you were, whatever memory you carried, seemed swallowed and gone, and that led scientists to a chilling belief about these objects. They started to think black holes weren't just traps, they were shredders. Machines that took anything at all and erased its very identity, blending every possible thing into the same featureless dark. Here's a fact about black holes that sounds too simple to be true. From the outside, they are almost boring. You can describe a black hole completely with just 3 numbers. That's it. 3 numbers. Its mass, how heavy it is, its spin, how fast it turns, and its charge, its electric pull. Give a scientist those 3 things, and they can tell you everything measurable about that black hole. Its size, its shape, its gravity, all of it. Physicists have a funny name for this rule. They call it the no-hair theorem. The idea is that black holes have no extra details, no bumps, no features, nothing to grab onto, like a perfectly smooth, bald bowling ball. No hair. Now think about what that really means, because it's disturbing. Take a star made of hydrogen gas, weighing as much as 10 suns. Drop it into a black hole. The black hole gets a little heavier. Now take a cloud of dust, or a planet made of iron, or a spaceship, or a library full of books, each also weighing as much as 10 suns. Drop each one in. Every single time, the black hole changes in exactly the same way. It just gets 10 suns heavier. The star The dust, the iron planet, the spaceship, the library, they all leave the identical mark. From the outside, you could never tell which one you threw in. The black hole looks exactly the same no matter what it ate. Feel the horror in that. The books had words. The spaceship had blueprints. The star had a swirling recipe of elements. All of that rich, specific detail seemed to get blended into the same smooth nothing. The black hole erased what made each thing unique and kept only the weight. Picture a paper shredder, but a perfect one. A normal shredder leaves strips you could tape back together with enough patience. This imaginary machine grinds everything into identical grey powder. Feed it a love letter, a treasure map, or a phone book, and you get the same pile of dust every time, with no way to ever tell them apart. That's what black holes seem to do to reality. For years, this felt fine to scientists. It even seemed elegant. Black holes were the great simplifiers, the ultimate erasers, taking the messy complexity of the universe and smoothing it into 3 plain numbers. But remember what we learned at the very start. The universe is supposed to keep a perfect memory. Nothing should ever be truly erased. Every burned page, every shattered glass, still holds its record in the scramble of its particles. That was the sacred rule. And here were black holes, seeming to break it without a care. Throw a book in, and the book's information looks simply gone, not scrambled and recoverable. Gone, blended into 3 numbers that could never tell you what had fallen in. Most scientists shrugged this off at first. The stuff is still in there, they figured. It fell down to the singularity and got locked away. Hidden, sure, but not destroyed. As long as the black hole exists, the memory could be thought of as trapped inside, safe behind the door. That comfort rested on one quiet assumption. It assumed the black hole would last forever, a permanent vault, holding its secrets for all time. Then, in the 1970s, a young physicist in a wheelchair did some math that nobody expected, and what he found turned the whole picture upside down. Black holes, it turned out, were hiding a secret glow. In the early 1970s, a young British physicist named Stephen Hawking set out to prove something about black holes. He was studying the edge, the event horizon, expecting to confirm what everyone already believed, that black holes only grow, that they swallow and never give anything back. His own math told him he was wrong. The equations kept insisting on something impossible. Black holes, the darkest objects in the universe, the perfect traps that light itself cannot escape, were faintly glowing. They were leaking energy out into space, a whisper of radiation, seeping from the edge of the void. Hawking didn't believe it at first. It sounded absurd. How could anything come out of a place defined by nothing coming out? He checked and rechecked, hunting for the mistake. There was no mistake. The glow was real, hidden in the math all along. Today we call it Hawking radiation, and it changed everything we thought we knew. To feel how shocking this was, remember the whole point of a black hole. The event horizon is a one-way door. Escape velocity beats light. Nothing gets out. That was the entire idea. Rock solid for decades. And now the math said, a black hole slowly, quietly shines, like an ember glowing in the dark. The glow is unbelievably faint. For a normal black hole, one made from a collapsed star, the radiation is so weak it's colder than the emptiest space between galaxies. It's a temperature just a hair above the coldest possible cold. You could never see it with your eyes or catch it with any telescope we have. But faint is not the same as zero, and that tiny difference from zero broke the old story wide open. Here's the strangest twist. Smaller black holes glow brighter and hotter than big ones, backwards from what you'd guess. A giant black hole in a galaxy's core barely glows at all, colder than ice, dimmer than a whisper. But a tiny black hole would blaze. If you could make one the size of an atom, it would pour out heat like a furnace. The smaller they get, the fiercer they shine. This flipped the black hole from a dead, silent pit into something almost alive. It has a temperature. It gives off light. It behaves, in a spooky way, like a hot coal cooling in the night air. And that raised a question that should make your skin prickle. If a hot coal glows because it's slowly burning away its own energy, then what happens to a black hole that glows? If it's leaking energy into space, drop by drop, then that energy has to come from somewhere. It has to be paying a price. The black hole is spending itself. Every flicker of that faint glow costs it a tiny piece of its own mass. The perfect eternal vault, the thing everyone assumed would last forever, was actually draining away the whole time. Hawking had found a crack in the idea that black holes are permanent. And once that crack appeared, the comfortable answer to the memory problem started to crumble. Because scientists had told themselves the information was safe, locked inside forever. That word forever was now in serious trouble. But to see why this glow is so dangerous to the memory of the universe, you first have to understand a deeper riddle. Where does the glow actually come from? Nothing is supposed to leave a black hole, so how does the light get out? Nothing escapes a black hole. That's the whole rule. So, how on earth does a black hole glow? Where does Hawking's radiation come from, if not a single thing can climb out of the trap? The answer hides in the strangest fact about empty space. Empty space is not actually empty. This sounds like a riddle, but it's real physics. Down at the tiniest scales, the vacuum of space is restless and bubbling. All the time, everywhere, tiny pairs of particles pop into existence out of nothing, flicker for the briefest instant, then crash back together and vanish. They appear and disappear so fast that we normally never notice. Scientists call them virtual particles. Picture the ocean surface, always fizzing with tiny bubbles. Each bubble forms, exists for a blink, then pops and is gone. Empty space fizzes like that, constantly, with pairs of particles, one with normal energy, its partner a kind of mirror image. They're born together, and almost instantly, they find each other again and cancel out. The books stay balanced. It's as if nothing ever happened. Now bring this fizzing right up to the edge of a black hole, to the event horizon itself. A pair of these particles pops into being, one just outside the door, one just inside. Normally they'd snap back together and vanish, but here, something interrupts them. The one born inside the horizon falls in. It's trapped, gone forever, dragged down toward the center. Its partner, born just outside, is free. With nothing left to cancel it, that outside particle goes flying off into space, becoming real. To a distant observer, it looks like the black hole just spat out a particle. That escaping particle is the glow. That is Hawking radiation. But here's the part that matters most. Where did the energy for that escaping particle come from? It couldn't come from inside the black hole, since nothing crosses the door outward. So, the universe does its bookkeeping in a sneaky way. The particle that fell counts as negative energy. When it drops into the black hole, it actually subtracts a tiny bit from the black hole's mass. Read that again, because it's the key to everything. The black hole gives off light, and the price it pays is a sliver of its own mass, carried off by the particle that escaped, balanced by the negative one that fell in. The glow is powered by the black hole slowly eating itself. So, the trap that swallows everything has finally started to give something back. But what it gives back is bizarre. The escaping particles come from the fizz of empty space right at the edge. They carry energy, and they carry away mass. What they seem to carry is random noise, shaped only by the black hole's temperature. That last point is a ticking bomb, and we'll come back to it. For now, hold on to the mechanism. Empty space bubbles. A pair splits at the horizon. One falls in and drains the black hole. One flies free as a glimmer of light. Repeat, over and over, for ages. And there's the danger, hiding in plain sight. If every flicker of that glow steals a piece of the black hole's mass, then the black hole is not sitting still. It's shrinking. Slowly, particle by particle, the vault is losing weight, which means these monsters, the objects everyone believed would outlast the stars themselves, are quietly counting down toward an ending nobody saw coming. A black hole is dying, Right now, every black hole in the sky is slowly losing weight, flickering its faint glow into the dark, shrinking toward an ending. The greatest traps in the universe are on a countdown clock. We just saw why. Every particle of Hawking radiation that escapes carries off a tiny piece of the black hole's mass. Bit by bit, the vault leaks. And as it loses mass, something disturbing kicks in. Remember the backwards rule from before? Smaller black holes glow hotter and brighter than big ones. So, as a black hole shrinks, it doesn't fade away gently. It heats up, and hotter means it leaks even faster, which makes it smaller, which makes it hotter still. The dying speeds up as it goes, racing toward a finish. Think of an ice cube melting on a hot sidewalk. As it gets smaller, more of its surface is exposed, so it melts faster and faster near the very end. A black hole does something like that, except the melting turns violent as the finish approaches. The final moment is explosive. In its last split second, the black hole is tiny and blazing hot, dumping the last of its energy in a burst of radiation. After holding its secrets for an unimaginably long time, the black hole finishes with a flash and is simply gone. The vault doesn't just open, it disappears entirely. Now, before you worry about the black holes out there tonight, here's the catch. This takes an absurdly long time, insanely long. A black hole made from a dead star would take vastly longer to evaporate than the current age of the universe. We're talking a number so huge, it barely means anything. Written out, it would have more digits than there are grains of sand on every beach on Earth many times over. To put it another way, the universe is around 14 billion years old. A star-sized black hole needs to survive countless trillions of times longer than that before it finally winks out. Every black hole we can currently see is so young by comparison that it has barely lost a whisper of its mass. They're all still growing, feeding faster than they leak. But time is patient, and the universe is in no hurry. Fast forward far enough, past the death of the last stars, past the age when galaxies go dark and cold, and eventually even the black holes must pay. One by one, across an ocean of time, they will heat up, shrink, and burst into their final flash. In the deep future, the last black hole in existence will flicker out, and the cosmos will hold none at all. So, black holes are temporary, after all. Long-lived beyond imagining, yes, but not eternal. And that single word, temporary, is where the entire nightmare snaps into focus. Because remember the comfort scientists clung to. When a book fell into a black hole and its information seemed to vanish, they told themselves it was fine. The memory wasn't destroyed. It was just locked inside, hidden away, safe behind the door for all time. That excuse only worked if the door stayed shut forever. And now we know it doesn't. The door doesn't just open. The whole vault vanishes in a flash of light. So here is the question that has haunted physics for 50 years. The black hole is gone, truly gone. Everything that ever fell inside it, every book, every star, every memory, went down with it. Where did all of it go? The trap has finally sprung shut. A black hole that spent ages swallowing stars, planets, light, and secrets has flickered its last glow and vanished in a final burst. Nothing is left where it used to be, just empty space and a fading puff of radiation drifting off into the dark. And now we face the question that keeps physicists awake at night. Everything that fell in is gone. So where did the information go? Let's line up the clues, because they lead somewhere terrifying. Clue 1. A black hole ate a library, a star, a spaceship, whatever you like. All of that had rich, specific detail. The words in the books, the elements in the star, the blueprints in the ship. That detail is the information, the memory of what those things were. Clue 2. From the outside, the black hole hid all of that behind 3 plain numbers: mass, spin, charge. The specific details were sealed away, seemingly locked inside the vault. Clue 3. The black hole slowly leaked away as Hawking radiation, then vanished completely. And here's the killer. That radiation comes from the fizz of empty space at the horizon. It's shaped only by the black hole's temperature. It carries energy and mass, but as far as anyone could tell, it carried no memory of what fell in. Put those clues together, and you get a horror story. The information went into the black hole. The black hole turned into featureless radiation and disappeared. So the information came out as meaningless noise, blended into a glow that looks the same no matter what got eaten. Picture it this way. You burn a book, but the smoke still holds the scrambled memory of the words. Painful to recover, but possible in principle. Now imagine burning the book and having the smoke come out as pure, blank, identical fog every single time, no matter which book you burned. The library, the phone book, the love letter, all producing the exact same featureless cloud. The memory would be truly, completely gone. That's what a black hole seemed to do. It took the perfectly recorded past and erased it, deleted it from reality. Not hidden, not scrambled, not locked away. Erased. Some scientists tried to wriggle out of it. Maybe the information sneaks out in the glow somehow, hidden in a pattern too subtle to see? But Hawking's own math said no. His calculations showed the radiation depended only on the black hole's size and temperature. Nothing else. The specific stuff that fell in left no fingerprint. Two black holes that ate wildly different things would glow in the exact same way and vanish identically. Maybe the information stays behind in a tiny leftover crumb, but the math said the black hole vanishes completely, leaving nothing but the fading radiation. No crumb, no hiding place, no safe. Maybe it fell through to some other universe? That's just moving the problem somewhere we can never check, and most scientists refuse to accept an answer they can never test. Every escape route seemed blocked. The information went in. The black hole erased it and died. The universe forgot. And that word, forgot, should send a chill through you. Because we started this whole journey with a sacred promise. The universe keeps a perfect memory. Nothing is ever truly lost. That promise is the foundation everything else in physics stands on. Black holes were now stomping all over it. And when the world's smartest physicists saw what this really meant, they didn't just frown, they panicked. When physicists fully understood what black holes seemed to be doing, they didn't shrug it off, they panicked. Because this wasn't a small crack in a corner of science. It was a hammer swinging straight at the foundation of everything. To feel their fear, you need to meet the rulebook that black holes were breaking. It's called quantum mechanics, and it is the most successful, most precisely tested theory in all of human history. Quantum mechanics describes the world of the very small. Atoms, electrons, light, the tiny building blocks of everything. It's the reason your phone works, the reason the sun shines, the reason chemistry happens. Every prediction it makes has come true, over and over, to a stunning level of accuracy. Scientists trust it more than almost anything else they know. And quantum mechanics has one iron rule at its very heart. Information is never destroyed, ever. In this theory, the universe carries its full memory forward through time, perfectly preserved. Take the complete state of things right now, and the rules let you run them forward or backward without ever losing a scrap of detail. The books always balance. Nothing gets added from nowhere. Nothing gets erased into nowhere. Physicists have a fancy word for this promise. They call it unitarity. But the plain meaning is simple. Reality remembers. This is the same sacred promise from the very beginning of our journey. The burned page still hides in the smoke. The shattered glass still hides in its pieces. Quantum mechanics is where that promise lives, written into the deepest math we have. Now, watch the collision. A black hole eats a book. It glows, shrinks, and vanishes, leaving only featureless radiation that carries no memory of the book. The information is gone, erased, deleted from the universe. Quantum mechanics says that's flat out impossible. Information cannot be destroyed. Not scrambled, not hidden, but actually destroyed. It cannot happen. The rulebook forbids it in the strongest possible terms. And gravity, through Hawking's math, said it happens anyway. Feel the size of this problem. Two of the greatest theories in all of science, both tested to fantastic precision, both trusted completely, were now screaming opposite answers about the same event. Einstein's gravity said the information is destroyed. Quantum mechanics said that's impossible. They couldn't both be right. One of them had to be broken. This is why they panicked. It wasn't a puzzle about weird, faraway objects. It was a sign that something in our deepest understanding of reality was badly, deeply wrong. If black holes really erased information, then quantum mechanics, the crown jewel of physics, had a fatal flaw. And if quantum mechanics was safe, then something about our picture of black holes and gravity was broken instead. Imagine two master map makers, each certain their map is perfect, handing you two maps of the same city that disagree on every street. You can't drive both. Something is wrong with one of them, and you have no idea which. That was the state of physics. Two perfect maps of reality, pointing in opposite directions. Scientists gave this collision a name, the black hole information paradox, and it became one of the most important unsolved problems in all of physics, chewed on by the greatest minds for half a century. But this fight was about more than which theory wins. Because if information really can be destroyed, the damage doesn't stay locked inside black holes. It leaks out into everything. It would poison the very idea of a trustworthy past. And that would change what reality itself means to you. Why should you care if some faraway black hole forgets a book? It sounds like a problem for a few physicists with chalkboards. But the stakes reach all the way down to the ground you stand on, to the meaning of your own past. Here's what's really at risk. If information can be destroyed, even in one place, even inside black holes, then the universe stops being trustworthy. Think back to the perfect memory we started with. The whole reason science works is that the past leaves a record. Effects point back to causes. You can look at the world today and, in principle, read where it came from. That unbroken chain is what lets scientists explain anything at all. Break one link, and the chain frays for everyone. Because black holes aren't rare freaks in some distant corner. They're everywhere. They sit at the center of nearly every galaxy, including our own. New ones form whenever a big enough star dies. If these common objects can quietly delete pieces of reality, then the deletion is happening all over the universe, all the time. And it gets more personal than that. Quantum mechanics is the rulebook for every atom in your body, every ray of light in your eyes, every spark in your brain. If black holes prove that its most sacred rule can break, then that rule isn't really a rule at all. It's just a habit reality usually follows, until it doesn't. The foundation of all our physics would turn to sand. Play it out. If information can vanish, then the link between cause and effect isn't guaranteed anymore. The past becomes something the universe can lose. And if the past can be lost, then the future becomes truly unpredictable in a way far deeper than normal. It would mean the universe has holes in its memory, gaps where things happen that reality itself can no longer account for. Picture a detective at a crime scene. Every clue, every fingerprint, every footprint tells a story that points back to what happened. The detective trusts that the past left evidence. Now, imagine a world where clues could simply blink out of existence, leaving crimes with no trace they ever occurred. No detective could ever solve anything. The whole idea of evidence would collapse. That's what a leaky universal memory does to science. It erases the fingerprints of reality. There's an even wilder worry lurking here. Some physicists showed that if information could be destroyed inside black holes, the damage might not stay polite and contained. The math suggested it could spill over and wreck the balance of energy everywhere, in ways that would make the ordinary world behave in impossible ways. A broken rule in one place threatened to break things far outside the black hole too. The poison wouldn't stay in the bottle, so this was never a small, faraway puzzle. It was a threat to the belief that reality is consistent, that the past is real, that the universe keeps honest books. Everything scientists trust rests on that belief. Black holes were putting it on trial. The problem was so serious and so stubborn that the smartest people in physics couldn't agree on the answer. They argued for years. They split into camps. Some were sure the information had to survive. Others were just as sure it was truly lost. The disagreement grew so sharp and the two sides so confident that three of the most famous physicists alive did something bold about it. They made a bet, a real, written, signed bet with a strange and specific prize on the line. By the 1990s, the black hole information paradox had split the world's physicists into stubborn camps. Two of the greatest minds alive were so sure they were right that they decided to put their reputations on the line. In 1997, they made it official. They signed a bet. On one side stood Stephen Hawking, the man who started it all with his glowing black holes. Beside him stood another brilliant physicist named Kip Thorne, an expert on gravity and black holes who would later help discover ripples in space itself. These two bet that black holes truly destroy information, that the universe really does forget. Hawking believed his own math. The glow was featureless, the black hole vanished, and the memory was gone for good. Gravity wins, and quantum mechanics has to bend. On the other side stood a younger physicist named John Preskill, a leading expert in the quantum world. He bet the opposite. He said quantum mechanics could not be broken. Information had to escape somehow, hidden in the glow, even if nobody could yet explain how. The rulebook of the small would win in the end. This was a clash of the two great maps of reality, made personal, gravity versus the quantum, and instead of just arguing in papers, they wrote it down and signed their names, promising a prize to the winner. The prize is the best part. The loser would buy the winner an encyclopedia, a big reference book stuffed with facts, of the winner's choosing. Why an encyclopedia? Because it's packed with information, and you can always look up whatever you want inside it. In other words, from an encyclopedia, information can always be recovered. It was a joke and a jab, both at once. The perfect trophy for a fight about whether information survives. That signed bet became legendary. It turned a dense, mathematical puzzle into a human story, a friendly duel between titans, with the nature of reality itself as the referee. For years, scientists watched to see who would have to buy the book. But behind the fun of the bet sat a deadly serious split, and it framed the whole search for an answer. Because if you laid out the possibilities plainly, the escape routes were few. Either the information is destroyed, and Hawking and Thorne win, or it survives somehow, and Preskill wins. And if it survives, there were only a handful of ways it could pull off that trick. This is the fork in the road where the whole story branches. For the next stretch of our journey, we're going to walk down each possible answer, one at a time. Each one sounds impossible in its own way. Each one asks you to give up something you thought was solid, and only one of them turns out to match what the deepest math finally revealed. The first path is the darkest. It's the one Hawking himself first believed, and it takes the paradox at face value. It says, stop trying to save the information. Stop looking for the trick. Maybe the terrifying answer is simply the true one. Maybe the information really is destroyed. Maybe the universe really does forget. Maybe the sacred rule of quantum mechanics, the promise that reality remembers everything, is just plain wrong, and we have to learn to live in a cosmos that can lose its own past. It's a bleak idea, and as we're about to see, it comes with a problem so severe that it nearly destroys the whole universe. Let's start with the darkest answer, the one Stephen Hawking himself first believed. It takes the nightmare at face value and says, simply, accept it. The information really is destroyed. The universe really does forget. Quantum mechanics, the sacred rule book, is just wrong on this one point, and we have to swallow it. At first, this feels almost brave. The math of Hawking's glow was clear. The radiation looked featureless. The black hole vanished. So why twist ourselves into knots trying to save the information? Maybe reality is telling us the truth straight up. Black holes are where memory goes to die, and we should believe our own equations. For a while, this was a serious position held by serious people. If gravity and the quantum disagree, they reasoned, then maybe gravity wins here, and quantum mechanics needs a small fix. A crack in the rulebook, allowing information to be truly lost inside these extreme objects. Then other physicists did the math on what that fix would actually cost, and what they found was horrifying. Here's the problem. In quantum mechanics, all the rules are tightly woven together, like threads in a single piece of cloth. The promise that information survives isn't a loose decoration you can snip off. It's stitched into the very fabric. Pull that one thread, and the whole cloth starts to unravel. In particular, they showed that if you allow information to be destroyed, you also break the careful balance of energy in the universe, and not gently. The math said that a universe where information can vanish would be a universe where energy could appear from nowhere, wildly and violently, everywhere at once. Think about what that means. Empty space, the air in your room, the vacuum between the stars, would boil with energy pouring out of nothing. Everything would heat up to impossible temperatures almost instantly. The ordinary, calm world we live in simply could not exist. It would cook itself in a flash. Picture a sweater with one loose thread. You think you can just snip it off to tidy up. But that thread is the one holding the whole sweater together, and the moment you cut it, the entire thing unspools into a pile of yarn in your hands. Trying to remove just the information rule from quantum mechanics does that to reality. You reach in to fix one small thing, and the whole universe comes apart. So the bleak answer had a fatal flaw. Letting black holes destroy information doesn't just cost you one rule. It threatens to make the everyday world impossible. And since the everyday world clearly does exist, since your room is not boiling with infinite energy right now, this answer looked deeply, dangerously wrong. That's a powerful clue. It suggests that quantum mechanics, with its promise of perfect memory, cannot simply be tossed aside. The rulebook is too tightly built. Break it here, and it breaks everywhere, and everywhere is fine. So the information probably survives after all. Preskill might be right, but saying the information survives is easy. Explaining how is the hard part. Because Hawking's math still stood there, stubborn as ever, showing a featureless glow that seemed to carry no memory at all. If the information gets out, it has to hitch a ride on that glow somehow in a way nobody could yet see. So the next answer tries exactly that. It asks a daring question. What if the escaping radiation isn't as blank as it looks? What if the memory of everything that fell in is sneaking out, hidden in the glow, written in a code too subtle for anyone to have cracked? If the information can't be destroyed, then it has to get out somehow. And there's only one thing leaving a black hole. The glow, the faint Hawking radiation, drifting off into space as the black hole shrinks. So the second answer makes a daring bet. The memory of everything that fell in is sneaking out, hidden inside that glow, written in a code too subtle for anyone to read. At first, this sounds like the obvious fix. Of course, the information comes out in the radiation. Where else would it go? But remember why this is so hard. Hawking's own math showed that the glow is featureless. It depends only on the black hole's temperature and size, nothing else. Two black holes that ate wildly different things would glow in the exact same way. The radiation looked like pure random noise, carrying no fingerprint of what fell in. So this answer needs a miracle. It needs the glow to be secretly full of hidden patterns, even though the simple math says it's blank. The clever idea is that the information isn't stored in any single particle of radiation. It's spread across all of them, hidden in the subtle relationships between them, the connections, the way each particle relates to every other particle it escaped with. Picture a giant crowd doing the wave at a stadium. Look at one single person standing up, and it means nothing, just a random person raising their arms. But zoom out, and watch how everyone moves in relation to everyone else, and a clear message appears, rolling around the whole stadium. The information lives in the pattern across the whole crowd, invisible if you only ever look at one person. The idea is that Hawking radiation works like that. Glance at one escaping particle and you see noise. But somehow, in the full pattern of all of them together, the memory is written. This gave scientists real hope. It let quantum mechanics keep its sacred promise. The information survives, spread thin across the entire globe, slowly leaking out over the black hole's long life until the last flicker carries the last piece. When the black hole finally vanishes, everything it swallowed has technically been handed back to the universe, coded into the radiation, memory preserved, rulebook safe. But there was a monstrous problem standing in the way, and it nearly sank the whole idea. To smuggle the information out in those hidden patterns, the escaping radiation would need to be deeply connected to something. And here's the trap. The math seemed to demand that each escaping particle be strongly linked to two different things at once. It had to be linked to its partner that fell into the black hole, and it also had to be linked to all the other radiation that already escaped to help carry the shared message. That double linking sounds harmless. It is not. There's a deep iron law in quantum physics that flat out forbids a single particle from being that strongly connected to two separate things at the same time. It's one of the strictest rules in the entire rulebook, and this escape plan seemed to smash right into it. So the second answer, beautiful as it was, hit a wall. To save the information, it seemed to break a different sacred quantum law instead. Trading one broken rule for another is no victory at all. Physicists were stuck between rules that couldn't all be true, and that suffocating trap, where every path breaks something you swore you'd protect, is exactly what set the stage for the next answer, and for the strangest idea yet. But first, one more escape route remained. One last simple hope that the answer was hiding somewhere much smaller. Before we reach the truly strange ideas, there's one more simple hope to try. The third answer, and it's the coziest of them all. It says maybe nothing really vanishes because the black hole never fully disappears. Maybe it leaves something behind, a tiny leftover seed that holds the entire memory of everything that fell in. The thinking goes like this. The scary part of the story was the ending, where the black hole shrinks down to nothing and pops out of existence, taking its secrets with it. But what if that ending is wrong? What if, instead of vanishing completely, the black hole stops shrinking when it gets incredibly small and just sits there forever as a tiny crumb? Scientists call this leftover crumb a remnant. Picture a giant bonfire that burns down through the night. In this idea, it never burns out completely. It always leaves one glowing ember behind, one that never quite dies. And inside that single ember, somehow, is locked the full memory of every log the fire ever ate. If that were true, the paradox would melt away. The information never gets destroyed because it never leaves. It stays tucked safely inside the remnant for all time. Quantum mechanics keeps its promise. The universe keeps its memory, and we don't have to believe in blank radiation secretly full of hidden codes. The answer is just a tiny box that holds everything. It sounds almost too easy, and that's the trouble. When physicists looked hard at this crumb, it started to sprout monstrous problems. Here's the first one, and it's a doozy. A black hole can be made from almost anything, and it can be any size. A small one, a giant one that ate a single star, one that ate a whole galaxy's worth of stuff. Each of those swallowed a different amount of information. Some swallowed a little, some swallowed a staggering, mind-crushing amount. Now shrink each one down to a tiny remnant. Every remnant is roughly the same tiny size, close to the smallest size anything can be. So you'd need these identical, minuscule crumbs to each hold wildly different amounts of memory. One crumb holds a little. Another crumb, exactly the same size, holds more information than you could fit in 1 billion libraries. That's the problem. You'd be asking for an object smaller than an atom to store an endless, unlimited amount of information inside it, a tiny box with infinite room. And in physics, that idea causes chaos. It breaks the sensible link between how big something is and how much it can hold. It leads to the same kind of energy nightmares we saw before, where impossible things start popping out of empty space. Picture a matchbox that you're told can hold the entire ocean, and also a swimming pool, and also a single drop, all in boxes that look exactly the same from the outside. It doesn't make sense. There's no way to tell them apart, and no room inside for what they're supposed to carry. The remnant idea asks reality to build boxes like that, and reality refuses. So the cozy answer crumbled too. 3 escape routes tried, 3 walls hit. The information can't simply be destroyed, or the universe boils. It can't easily sneak out in the glow, or it breaks a sacred quantum law. It can't hide in a tiny crumb, or the crumb holds impossible infinities. Every straightforward path was blocked, and that total dead end forced physicists to do something desperate. They had to stop patching the old picture and question something far deeper. Something about where a black hole's memory is truly stored. And the clue they found pointed to the most unexpected place imaginable, the thin surface of the black hole, not the space inside it. Every dead end pointed to the same buried mistake. Physicists had been picturing a black hole's memory in the wrong place. They kept imagining everything piled up inside, down at the center, crushed into the singularity. But the clue that finally cracked the paradox said something bizarre. The memory doesn't live inside the black hole at all. It lives on the surface. Stop and picture how strange that is. You have a huge 3-dimensional black hole, a deep well of space with a center far below, and someone tells you that everything it ever swallowed, every book, every star, isn't recorded down in the depths. It's written on the thin skin at the edge. On the event horizon itself, it's like being told that everything inside your house, every piece of furniture, every person, every object in every room, is somehow fully recorded on the outside walls, not inside, on the surface wrapping around it. This weird idea didn't come from nowhere. It grew out of a discovery about how much a black hole can actually hold. And that discovery started with a young scientist asking a childish-sounding question. How much memory can you cram into a black hole before it's full? To answer that, you first have to know how information gets measured at all. Scientists measure it a lot like messiness. A neat, orderly thing carries little information. A wildly complex, jumbled thing carries a lot. The fancy word for this messiness is entropy. The more entropy something has, the more hidden detail it holds, and the more memory it takes to fully describe it. Now here's the setup for the breakthrough. Toss a book into a black hole. The book had entropy, a certain amount of messiness and detail. Once it falls past the horizon, you can't see it anymore. So, from the outside, did the messiness of the universe just drop? Did the total amount of disorder go down when the book disappeared? That might sound harmless, but it would break one of the most ironclad laws in all of physics. A law that says the total messiness of the universe can never decrease. It can only stay the same or grow. This law has never once been seen to fail. It's the reason heat flows from hot to cold, the reason time seems to move forward, the reason a broken egg never unbreaks. If a black hole let you hide messiness by swallowing it, you could break that sacred law over and over. Throw all your disorder into a black hole, and the universe looks tidier than the law allows. Something had to give. A young physicist stared at this puzzle and came up with a bold fix. He said the black hole must carry its own messiness, its own entropy, to make up for everything it eats. The disorder isn't lost. It gets added to the black hole's account. The books stay balanced. But then came the real shock, the part that changed everything. When he worked out how much entropy a black hole carries, the answer didn't depend on the black hole's volume, on how much space was inside it. It depended on the area of its surface, on the size of its skin, and that single strange fact would blow the doors off our picture of reality. The young physicist was named Jacob Bekenstein, and his answer rewrote the rules. A black hole's memory, its hidden messiness, its entropy, isn't set by how much room it has inside. It's set by the area of its surface, by the size of its event horizon. Sit with how backwards that is. Everything in your everyday life scales with volume. A bigger box holds more stuff because it has more room inside. Fill a swimming pool, and what matters is how deep and wide and long it is. The whole three-dimensional space. Double the size in every direction, and you get 8 times the room to fill. Black holes refuse to play by that rule. Their memory scales with surface, not with the space inside. Grow a black hole, and its capacity to hold information rises with the area of its skin, like the outside of a balloon, not with the swollen space within. Here's a way to feel the strangeness. Imagine you want to store a huge library. Everywhere else in the universe, you'd fill a room, using up all the space inside it, shelf after shelf, front to back. But a black hole stores its library as if you could only write on the windows, only on the surface. And somehow that surface holds every last book. Bekenstein figured this out by carefully tracking what happens each time a black hole swallows something. Every time it eats a bit of matter, its surface grows by a tiny, precise amount. And that growth in surface exactly matches the messiness it just swallowed. The skin keeps a perfect running tab. Nothing gets lost. The books balance, written on the surface. Then another physicist tied it all together. When Hawking worked out his glowing radiation, his math locked in the exact link between a black hole's surface area and its entropy. It confirmed Bekenstein was right, and it nailed down the precise recipe. The amount of memory a black hole can hold is set by the area of its horizon, measured in impossibly tiny squares. And these squares are unbelievably small. Each unit of information takes up a patch of the horizon so tiny it's near the smallest length that has any meaning in physics. Which means even a modest black hole has a staggering, colossal amount of memory written on its skin. Far more than could fit in every computer humanity has ever built, many times over. The surface of a black hole is the most crammed storage in the universe. Now step back and feel the size of this clue. We've learned that a black hole's entire memory, everything it ever ate, is measured by its surface, not its insides. That hints at something wild. Maybe the information isn't down in the depths at all. Maybe it's smeared across the two-dimensional skin at the edge, and the deep interior is, in some sense, a kind of illusion painted from that surface. That thought sounds like madness. A three-dimensional world stored on a flat two-dimensional boundary. But it grew into one of the most powerful ideas in modern physics, an idea that reaches far beyond black holes and reaches all the way to you. Because if a black hole's insides are written on its surface, then maybe everything is. Maybe the whole universe is playing the same trick. Follow the clue where it leads, and you arrive at one of the wildest ideas in all of science. If a black hole's entire memory is written on its two-dimensional surface, then the three-dimensional inside might be a kind of projection, a picture painted from information stored on the edge. Physicists gave this a name that fits perfectly: the holographic principle. You already know what a hologram is. It's that shiny sticker on a credit card or a trading card that looks flat but shows a full three-dimensional image when you tilt it. A solid-looking scene with depth and roundness, all stored on a flat surface. The 3D you see is encoded in the 2D you're holding. The holographic principle says reality might work the exact same way. It says all the information needed to describe a chunk of three-dimensional space, everything happening inside it, can be fully captured on the two-dimensional boundary that wraps around it. The inside is the hologram. The surface is where the real data lives. Let that reshape how you see a black hole. The three-dimensional pit, with its deep interior and its center far below, might be a projection. The true, complete description sits on the flat horizon, the skin. The inside is like the popping image on the credit card. It looks solid and deep, but the actual information is written on the surface, wrapping it. This cracked the information paradox wide open. If everything that falls into a black hole gets recorded on the surface, then nothing is truly lost when things fall in. The memory is sitting right there on the horizon, held in that surface. And when the black hole slowly glows away, that surface shrinks and hands its stored information back out into the radiation. Memory preserved. The universe keeps its books. But the holographic principle did something much bigger than solve one puzzle about black holes. It planted a shocking suspicion in the minds of physicists. If a black hole's insides are secretly a projection of its surface, then why stop at black holes? Look around the room you're in. It feels solidly three-dimensional: depth, height, width. You can walk across it. But the holographic principle whispers a jarring possibility. Maybe all of it, the room, the depth, the space itself, is a projection too. Maybe the real information describing your world lives on a distant two-dimensional surface, far away at the edge of everything, and the rich 3D life you experience is the hologram it paints. It sounds impossible. It sounds like a fever dream. But this idea turned out to be more than a wild guess. Scientists found a specific, detailed case where they could prove it worked, with rigorous math, exactly, in a toy universe built for testing. And that success turned the holographic principle from a strange hunch into one of the most trusted tools in modern physics, which forces a question that might make your head spin. If it works for black holes, and it works in the math, then how far does it go? Could the trick behind a black hole's memory be the same trick behind everything you see and touch? Could your entire universe be a hologram? Let's chase the wildest version of the idea all the way to the edge. If the inside of a black hole is a hologram painted from its surface, then maybe your whole universe is doing the same thing. Maybe everything you see, touch, and are is a projection from a distant two-dimensional boundary. This isn't a stoner's late-night ramble. It's a serious proposal that top physicists have chased with hard math for decades. The claim is startling. The three-dimensional world you live in, with all its depth and solidity, could be encoded on a faraway surface at the edge of the cosmos, and the rich, deep reality you move through would be the hologram that surface projects. The breakthrough came in the late 1990s, when a physicist named Juan Maldacena found something astonishing. He built a toy universe in his math, a carefully designed model cosmos, and he proved that two totally different descriptions of it were secretly the exact same thing. Here's the magic. One description was a three-dimensional world with gravity inside it, black holes and all. The other description was a flat, two-dimensional world sitting on the boundary, with no gravity at all, just particles dancing on a surface. These two pictures looked nothing alike. One had gravity and an extra dimension. One didn't, yet the math showed they were perfectly, completely equivalent. Anything happening in the 3D world with gravity had an exact match in the 2D world on the edge. Picture a movie playing on a screen. The film bursts with three-dimensional worlds, deep landscapes, characters moving through space. But all of it is stored as a flat pattern on the surface of the screen, or as code on a disk. The depth is real to your eyes, yet the actual information is flat. Maldacena showed that a universe with gravity can work exactly like that. The 3D world, with all its depth, is the movie. A flat surface at the boundary holds the code. This was a stunning success. It gave physicists a working example, proven in detail, where a whole universe with gravity was truly a hologram of a simpler world without gravity, living on its edge. Suddenly, the wild idea had solid ground under it. This tool became one of the most used and trusted ideas in all of theoretical physics, cited in thousands upon thousands of studies. Now, a careful note, because trust matters here. The toy universe Maldacena used isn't exactly our universe. His model cosmos has a different shape than the real one we live in. So this is not yet proof that you are a hologram. It's proof that holographic universes are possible. that the trick is real and self-consistent in at least one kind of cosmos. Whether our actual universe works this way is still an open question scientists are chasing hard. But even as a possibility, it changes everything. It means the paradox-smashing idea that information lives on surfaces isn't a weird black hole quirk. It might be the deepest truth about how reality stores itself. Depth might be an illusion, surface might be everything, and this powerful tool did more than hint that we're holograms. It handed physicists a brand new way to attack the black hole paradox, because now they could take a confusing black hole with its impossible interior and translate it into the simpler flat world where no information could ever hide. If they could just read the answer over there, they could finally learn the fate of everything a black hole eats. But before that translation could crack the case, physicists ran into a paradox inside the paradox. A situation so strange it seemed to demand that two different people see two different, contradictory truths, and both be completely right. The holographic idea gave physicists hope, but the black hole had one more twist waiting. To save the information, scientists were forced into a claim so strange it sounds like a magic trick. Two different observers, watching the same person fall into a black hole, would see two completely different stories. And both stories would be true. Remember the falling friend from earlier? Let's bring them back, because now they cause real trouble. You watch from a safe distance as your friend falls toward the black hole. From your view, they never actually cross the horizon. Their fall slows, their light reddens, and they freeze at the edge, smeared across the surface, fading but never quite gone. In fact, in this picture, the intense glow of the black hole would eventually burn them up right there at the edge, and their information would join the Hawking radiation leaking out. But your friend tells a completely different story. From their point of view, they sail straight through the horizon without feeling a thing. No burning, no freezing, no smear. They cross the one-way door alive and whole, and only meet their doom much later, deep inside, near the center. So, which is it? Did your friend burn up on the surface, their information staying outside in the glow? Or did they pass through the horizon intact, carrying their information inside? These two stories flatly contradict each other. Your friend cannot both be vaporized at the edge and sailing through unharmed. It seems like a deal breaker. Physicists found a daring way out, and they called it complementarity. The escape is this: no single observer can ever see both stories at once. And if you can never catch the contradiction, then maybe there is no contradiction. Think about it. To see your friend burn up at the edge, you have to stay outside. To see your friend pass through unharmed, you have to fall in with them. You cannot do both. If you stay outside, you'll never witness the peaceful crossing. If you jump in, you'll never witness the burning. The two truths are kept in separate rooms, and no one holds a key to both. Here's a loose comparison. Think of a coin spinning on a table. From directly above, you might see only heads. From the side, you might see only the thin edge. Two observers describe the same coin in ways that don't match, and neither can stand in both spots at the same instant. The catch with the black hole is deeper because the horizon actively prevents anyone from ever comparing notes. The one-way door guarantees the two witnesses can never meet to argue. It's a wild trick. Reality serves up two contradictory accounts and stays consistent only because it forbids anyone from ever seeing both. The information is outside, in your story. The information is inside, in your friend's story. And because those two people can never compare notes, the universe never has to pick. For a while, complementarity felt like a clever patch that might actually hold. It let the information stay outside, safe in the glow, while your friend still felt nothing crossing the horizon. Everyone gets a self-consistent tale. But then a small group of physicists poked at this idea hard, following it to its logical end. And what they found didn't smooth things over. It lit a wall of fire, right at the edge of the black hole that threatened to burn the whole peaceful picture to ash. In 2012, 4 physicists poked at the black hole so hard that it seemed to catch fire. They were testing the comfortable idea that a falling friend feels nothing crossing the horizon, and their result was so alarming it earned a frightening name: the firewall. Here's the trap they found. To keep quantum mechanics happy and let information escape in the glow, they followed the rules carefully, step by step, and the rules led them to a shocking conclusion. Instead of a gentle, unnoticeable crossing, anything reaching the event horizon would slam into a raging wall of energy, a blaze hot enough to incinerate you the instant you touched it. This wrecked everything scientists thought they knew about the edge. For decades, the whole point of the event horizon was that it feels like nothing. Einstein's theory insists on it. If a black hole is big enough, you drift across the horizon, completely unaware. No jolt, no heat, no sign at all. The edge is supposed to be a calm, invisible line. The firewall says otherwise. It says the edge is a deadly inferno, and crossing it means instant destruction. No peaceful fall, no sailing through unharmed. You'd hit a sheet of fire and be gone in a flash. Why would fire appear at all? It traces back to those entangled particle pairs that make the glow. To let the escaping radiation carry information out, the old bonds between particle pairs at the horizon have to be violently broken. And in quantum physics, snapping those bonds releases energy. Snap all of them, all across the horizon, and you get a colossal blast of energy blanketing the edge. A firewall. Feel the size of the problem now. Einstein's gravity says the horizon is calm and empty. Quantum mechanics, pushed to protect information, says the horizon is a wall of fire. Both cannot be true. Your friend cannot both drift through gently and burn to ash at the same edge. Picture a door you've walked through peacefully 1,000 times, and someone hands you proof that the door has secretly been a solid sheet of flame the entire time. That's the collision. Two trusted descriptions of the same doorway. One calm, one deadly, with no way to fit them together. The firewall turned a clever truce into open war. Complementarity had promised everyone a peaceful, self-consistent story. The firewall said no. Someone has to face the fire. Either the horizon burns, breaking Einstein's smooth space, or the horizon is calm, breaking the escape of information. Once again, two sacred ideas were pointing weapons at each other. This threw physics into fresh chaos. The firewall was deeply unwelcome. It meant that saving information might cost you the calm horizon that Einstein's theory demands. Nobody wanted a universe where black hole edges are hidden bonfires. Yet the logic was tight, and shrugging it off wasn't easy. The firewall forced everyone to stare at an ugly menu of choices. And every option on that menu meant giving up something physicists had sworn was untouchable. It sharpened the whole paradox into one brutal decision. To keep the memory of the universe, which cherished belief were you willing to burn? The firewall left physicists staring at a menu where every dish was poison. It boiled the whole paradox down to a brutal short list. 3 things they believed with all their hearts. And the firewall argument said, with cold logic, that you cannot keep all 3. At least one has to be thrown out. Pick your loss. Let's lay the 3 treasured beliefs on the table. The first is that quantum mechanics holds, so information escapes the black hole, the sacred promise. Memory is never destroyed. The glow must carry the record of everything that fell in. Give this up, and the universe forgets, and reality boils, as we saw before. The second is that the event horizon is calm, just like Einstein says. Fall toward a big black hole, and you feel nothing at the edge. No fire, no wall, no jolt. Empty space that happens to be a point of no return. Give this up, and you get the dreaded firewall, an inferno where Einstein promised smoothness. The third is that the ordinary laws of physics work normally in the space around a black hole, far from the center. No weird new effects out where things should be tame. Physics behaves out there the same way it behaves here, in your room. Give this up, and the reliable rules we count on start bending in places they never should. Now here's the cruel part. Each belief on its own seems obviously true, rock solid, untouchable. Quantum mechanics has never failed a test. Einstein's calm horizon is a direct result of the most successful gravity theory ever written. And the ordinary laws working in empty space far from the center is just common sense. You'd bet your life on any one of them, but the firewall argument proves something maddening. Hold all three at once, and they contradict each other. The math simply won't allow all three to be true together. It's like being handed three keys, each one guaranteed to fit the lock, and discovering that turning any two of them jams the third. Picture a stool with three legs, and someone proves that the three legs cannot all touch the ground at the same time. Push two down flat, and the third lifts into the air. There's no way to make the stool stand honestly on all three. That was the state of physics. Three trusted legs, and no way to rest on all of them. This is what made the firewall so vicious. It wasn't just one scary idea. It was a proof that our cherished beliefs were secretly at war, that we'd been holding contradictory things all along without noticing. Something we were sure of had to fall, and that turned the whole paradox from a puzzle into a crisis. Physicists split apart, each choosing a different leg to sacrifice. Some gave up the calm horizon and accepted the firewall. Some twisted quantum mechanics. Some questioned the ordinary rules far from the center. No one agreed. The war was on, and the smartest people alive couldn't find peace. To understand why the firewall's logic felt so impossible to escape, you have to meet the single quantum rule sitting at the very center of the trap. A rule so strict it acts like a law of loyalty between particles. Break it, and information can't escape. Keep it, and you get fire. It's the deepest key in the whole mystery. At the very heart of the firewall trap sits one strict quantum rule, and it has a surprisingly human name: the monogamy of entanglement. Understand this one rule, and you understand why the black holes seem to force fire at its edge. First, meet entanglement, one of the strangest facts in all of physics. Two particles can be linked in a way so deep that they act like a single connected thing, even when far apart. Measure one, and you instantly know something about the other. They share a bond that ordinary objects never have. Einstein himself found it so unsettling he called it spooky. Now here's the rule that matters. This deepest kind of entanglement is strictly one-on-one. A particle can share that maximum bond with only one partner at a time. Just one. It cannot be fully, maximally entangled with two different particles at once. The bond demands loyalty. That's why scientists nicknamed it monogamy. Like a partner who can only be fully devoted to one other, a particle can only be maximally linked to one other. Picture two dancers locked together in a dance so perfectly synced that each mirrors the other's every move. That perfect sync only works between two. A third dancer cannot join and be equally, perfectly synced with both at the same time. The perfect partnership is closed. Two, and only two. Now watch this rule spring the trap. It comes down to those particle pairs at the horizon that create the glow. When a Hawking particle is born at the edge, it starts out entangled with its partner, the one falling into the black hole. That bond is what a fresh pair has. Fine so far. But to carry information out of the black hole, that same escaping particle also needs to be entangled with all the radiation that left earlier. It has to join the big shared pattern that secretly holds the memory, the message spread across the whole crowd of escaped particles. There's the collision. The escaping particle needs to be fully entangled with its infalling partner, and fully entangled with the earlier radiation, both at once, two maximum bonds at the same time. And the monogamy rule flatly forbids that. A particle cannot be perfectly devoted to two partners. It has to choose. So something has to break. If the escaping particle stays bonded to the earlier radiation, so information can escape, then its bond with the infalling partner must snap. And snapping that bond, as we saw, releases energy. Do it for every pair across the whole horizon, and you get the firewall. The fire is the price of breaking monogamy. That's the deep engine under the whole crisis. The monogamy of entanglement, one of the strictest rules in quantum physics, seemed to make it impossible to have a calm horizon and escaping information at the same time. One bond too many, and reality catches fire. For years, this felt like an unbreakable wall. The logic was tight. The rule was sacred. Fire seemed unavoidable. But the answer, when it finally came, would arrive from the most unexpected direction imaginable. It came from an idea that sounded like pure science fiction. What if the two entangled particles are secretly connected by a tunnel through space itself? The way out of the firewall came from an idea so strange it sounds made up. What if two entangled particles, no matter how far apart, are secretly joined by a tiny tunnel through space? A microscopic wormhole, threading them together behind the scenes. First, meet the wormhole. It's one of the wildest predictions hiding in Einstein's theory of gravity. A wormhole is a shortcut through space, a tunnel connecting two faraway places. Imagine folding a piece of paper so two distant dots touch, then punching a hole between them. Instead of traveling the long way across the paper, you slip through the tunnel and pop out the far side instantly. That's a wormhole. Two separated spots, secretly linked by a bridge. For a long time, wormholes and entanglement seemed like completely different things from completely different corners of physics. Wormholes came from gravity, from Einstein's warping of space. Entanglement came from the quantum world of tiny particles. Nobody thought they had anything to do with each other. Then two physicists noticed something that made their jaws drop. The math describing a wormhole connecting two black holes looked suspiciously like the math describing two entangled particles. The two ideas, born in separate worlds, seemed to be secretly the same thing. This led to a bold and beautiful guess. Maybe entanglement just is a wormhole. Maybe every time two particles are entangled, they're connected by an unimaginably tiny wormhole, a secret bridge through space. When two particles share that spooky link, they aren't really separate at all. They're joined by a tunnel too small to ever see. Scientists gave this a short nickname. It says, wormholes equal entanglement. Feel how wild this is. That spooky bond Einstein hated, the one where two particles act as one across huge distances, might be a physical connection after all, not magic, not signals faster than light, a literal tunnel, stitching them together through the hidden fabric of space. Now watch how this melts the firewall trap. The problem was monogamy. The escaping particles seemed to need two separate bonds, one to its infalling partner and one to the earlier radiation, and that broke the one-on-one rule. But if entanglement is wormholes, those bonds aren't separate abstract links. They're tunnels through space, and tunnels can merge. They can join up into one connected geometry. So the two bonds that seem to fight each other might really be one big connected tunnel system, threading the inside of the black hole to the radiation outside. The infalling partner and the escaped radiation could be linked through the belly of the black hole itself, joined by wormholes into a single structure. If the connection is really one merged tunnel, then the monogamy rule isn't broken. There's no forbidden second bond. And with no broken bond, there's no snapped entanglement, and no firewall. The fire goes out. This was a stunning turn. A wild, science fiction sounding idea, tunnels through space, offered a way to keep the horizon calm and still let information escape. The two enemies might be secretly holding hands through a hidden bridge. And this hinted at something even bigger, something that reaches past black holes and touches the nature of space itself. If entanglement is really tiny wormholes, then maybe those threads aren't just decorations inside space. Maybe they're what space is made of. If entanglement is secretly tiny wormholes, tiny threads through space, then a breathtaking thought follows. Maybe those threads are not sitting inside space. Maybe they weave space into being. Maybe the smooth, solid space you move through every day is stitched together out of countless entanglement threads, like fabric woven from thread. This flips everything you assume about reality. You probably think of space as the stage, the empty container that everything else sits in, fixed, basic, just there. Distance and depth feel like the bedrock, the thing that was always around for stuff to happen in. The new idea says space is not the stage at all, it's the play. Space is something built, something woven, and the thread it's woven from is entanglement. Those quantum bonds between particles are the stitches. Pack enough of them together in the right pattern, and they knit into the smooth fabric we call space. Here's how physicists picture the weave. When two regions of space are strongly entangled, richly threaded together, they sit close, tightly connected, part of the same smooth cloth. When two regions share little entanglement, few threads between them, they sit far apart. So distance itself, the very idea of near and far, comes from how much entanglement connects things. More threads means closer, fewer threads means farther. Picture a sweater knitted from yarn. From a distance, it looks like one smooth, continuous sheet of fabric, but leaning close, and you see its really countless loops of thread, hooked together, stitch by stitch. Pull the yarn out, and the sweater vanishes. There's no sweater underneath the thread is the sweater. The idea is that space works the same way. Pull out the entanglement threads and space itself would dissolve. There's no smooth space underneath. The threads are the space. Scientists tested this idea in their holographic toy universes, the ones where a whole world with gravity lives as a projection on a flat boundary. And when they tinkered with the entanglement on the boundary, the space inside responded. Weaken the entanglement between two parts of the boundary, and in the 3D world inside, those regions drift apart. Cut the entanglement completely, and the space inside tears in two, ripping into separate pieces. The threads really did seem to be holding space together. Feel the size of this claim. It means gravity, space, distance, the whole stage of reality, might all rise up out of quantum entanglement. The bonds between tiny particles could be the loom that weaves the cosmos. Reality, at its deepest level, would be a tapestry of quantum threads, and everything solid we know would be the pattern they form. And this reaches straight back to our black hole. Because if space is woven from entanglement, then the inside of a black hole and the radiation outside and the tunnels between them are all part of one connected weave. That was the loophole that put out the firewall. The threads could merge into one fabric, and the monogamy rule could stay unbroken. But we still haven't seen the actual answer to the paradox. All of this, the surfaces, the holograms, the wormholes, the woven space, was building toward one concrete test, a specific shape the escaping information had to trace. If it truly escapes, get that shape right, and you prove the memory survives. Get it wrong, and the information really is lost. For 50 years, the whole argument had been fought with words and ideas, but there was a way to settle it with a hard, exact number, a specific shape, drawn on a graph, that would reveal the truth once and for all. Scientists call it the page curve, and it became the finish line for the entire paradox. Here's the idea behind it. Forget the philosophy for a moment and just track one thing as the black hole glows away. Track how much the escaping radiation secretly remembers. How much of the black hole's information is riding out in the glow at each moment. Plot that on a graph over the black hole's whole lifetime, from birth to final flash, and the shape of that line tells you everything. Two possible shapes, two possible fates. If Hawking was right and information is destroyed, the line only ever climbs. As the black hole glows, the radiation gets more and more scrambled, more disconnected from anything real, all the way until the black hole vanishes. The line goes up and never comes back down. At the end, you're left with a pile of radiation that remembers nothing. The information is gone. But if quantum mechanics is right, and information survives, the line has to do something very different. It has to rise at first, then bend, turn around, and come back down to zero by the time the black hole disappears. That turnaround is everything. The line rising, peaking, then falling back to zero means the radiation ends up carrying the full memory of everything that fell in. Nothing lost. The book's balanced. That turning point has a name: the page time. It's the moment, right in the middle of the black hole's life, when the memory stops scrambling and starts coming back out. The exact spot where the line bends from climbing to falling. If you ever see that bend, you've caught the universe keeping its promise. Picture pouring red dye into a glass of water. At first, the dye spreads and the water looks more and more mixed, more scrambled, harder to read. That's the line climbing. But now imagine that, halfway through, the dye slowly gathered itself back together and streamed back out into an eyedropper, leaving the water clear again. That impossible-looking return, the mixing reversing into clarity, is the falling half of the page curve. It's the information finding its way back out. A physicist named Don Page worked this out long ago. He said if quantum mechanics is truly safe, then the curve must bend. It must come back down. He didn't know how the information would escape. He just knew that if it does, the graph has no choice but to make that turn. The bending page curve became the fingerprint of survival, the exact signature that memory is preserved. So the whole 50-year war came down to one crisp question: which shape is real? The line that climbs forever and loses everything, or the line that rises, bends, and returns, saving it all? For decades, nobody could calculate it from the black hole's side. Hawking's math kept giving the rising line, the line of doom. To prove the information escaped, someone had to find where his calculation missed something and show the curve actually bends. And when the answer finally came, it arrived from the strangest place, a hidden piece of the black hole's inside that secretly belonged to the outside. The breakthrough that finally bent the page curve came with a strange and fitting name: islands. And the idea behind them is one of the most surprising turns in the whole story. It says that a piece of the inside of a black hole secretly counts as part of the outside. Sit with how odd that is. You have the inside of the black hole, deep behind the horizon, and you have the radiation far outside, drifting away. Everyone assumed those were totally separate. Inside is inside, outside is outside. The one-way door stands between them. The island idea shatters that clean split. It says that after the black hole has glowed for long enough, a chunk of the interior stops belonging to the black hole and starts belonging to the radiation instead. This inner chunk is the island. It's physically deep inside the black hole, yet it counts as part of the outside world, part of the escaping glow. How can a piece of the inside belong to the outside? Through exactly the woven threads we just met. The radiation far away is entangled with the interior, threaded to it through the hidden fabric of space, maybe through those tiny merged wormholes. Those connections stitch the far-off radiation to a deep inner region so tightly that the region effectively joins the radiation. Distance stops mattering. The thread is what counts, and the thread makes them one. When physicists finally included these islands in their math, everything changed. For decades, calculations of the radiation's memory left the islands out, because nobody knew they belonged. Leaving them out gave Hawking's answer, the line that climbs forever and loses all the information, the line of doom. But when they counted the islands in, the graph transformed. Early in the black hole's life, the island contributes nothing, and the line climbs as before. But past the halfway mark, the page time, a giant island suddenly switches on deep inside the black hole, and once you include everything that island secretly holds, the memory in the radiation stops rising. It bends, it turns over and starts falling, exactly as quantum mechanics demanded. The island was the missing piece. Counting it made the page curve bend the right way, all on its own, straight out of the math. The information wasn't lost after all. A big slice of it was hiding in that inner island, secretly belonging to the outside glow the whole time. Picture a prison that everyone believed was sealed shut, escape-proof, nothing ever leaving. Then someone discovers a hidden room deep inside the prison that, through a secret passage, actually opens onto the street outside the walls. Prisoners in that room were technically outside all along. The island is that hidden room, part of the black hole's inside that was quietly on the outside the entire time. This was a triumph. Using islands, physicists calculated the page curve straight from the black hole and got the bend, the return, the signature of survival. Quantum mechanics kept its promise. Information escapes. Hawking's original answer had missed these hidden rooms, and once they were found, the memory of the universe was safe. But saying an island belongs to the outside is a bold claim that needs backing. Where did these islands actually come from in the math? The answer ties every thread of our story together, and it comes from those tunnels through space we thought were pure fantasy. Where did the islands come from? What made a chunk of the inside secretly belong to the outside? The answer pulls together every strange thread of this whole story, and it comes straight from those tunnels through space we called pure fantasy, wormholes. When physicists did the deep calculation of the black hole's memory, they weren't just adding up the obvious stuff. They were using a powerful method that sums over every possible shape space could take. And when they let space take every shape it wanted, something unexpected showed up in the math on its own. Tiny wormholes, tunnels connecting the inside of the black hole to the radiation drifting outside. Nobody put those wormholes in by hand. They appeared by themselves, demanded by the calculation. The math insisted that the inside and the outside were secretly connected by these bridges through space. And those bridges were exactly what tied the far-off radiation to the deep inner island. The wormholes were the secret passages that made the hidden room open onto the street. This is the moment where the whole story clicks together. Remember the guess from before? That entanglement is secretly tiny wormholes? Here it was, showing up in a hard calculation, not as a dream but as a working part of the answer. The tunnels stitched the radiation to the island. The island bent the page curve. The bending curve proved the information escapes. Every piece locked into place, and wormholes were the glue. Let that settle. The thing that saved the memory of the universe was a network of tunnels through space, connecting the belly of a black hole to the faint glow escaping it. An idea that sounds like the wildest science fiction turned out to be the quiet hero of the most serious calculation in modern physics. Picture a spider web strung across a dark corner. From far away, you see only two things: the trapped bug deep in the center and the spider waiting at the edge. The threads between them are too thin to notice. But those invisible threads are what connect the two, what let a tug at the center be felt at the rim. The wormholes are those invisible threads, connecting the deep inside of the black hole to the radiation at the edge, too small to see but strong enough to carry the memory out. And here's the part that keeps physicists humble. These calculations show that the information escapes. They prove the page curve bends. They prove quantum mechanics keeps its promise and the memory survives. But they do it in a slightly sideways way, using clever math tricks and these summed up wormholes. They tell us, with confidence, that the information gets out. They don't quite tell us exactly how a single specific bit rides out in the actual glow. It's like having ironclad proof that a magic trick must have a hidden method, without being handed the full step-by-step secret of how the magician does it. We know the escape happens. We can even prove it must. The last fine detail of the mechanism is still being chased. Even so, this was enough to settle the oldest bet in physics. Enough to make one of the most famous scientists in the world stand up and admit, in front of everyone, that he had been wrong all along. In 2004, at a big physics conference in Ireland, Stephen Hawking walked to the front of the room and did something rare for any scientist, let alone the most famous one alive. He announced, in front of the whole world, that he had been wrong. For nearly 30 years, Hawking had insisted that black holes destroy information. It was his position, born from his own groundbreaking math about the glow. He had bet on it. He had defended it. But the mounting evidence, the holographic tools, the growing case that information leaks out in the radiation had finally changed his mind. So he conceded. He stood up and declared that he now believed black holes do not destroy information after all. The memory of the universe survives. The record leaks back out in the glow, however scrambled. Quantum mechanics keeps its sacred promise. Hawking had switched sides in his own war, and then he paid the bet. Remember the wager from years before, Hawking and Thorne against Preskill, with an encyclopedia on the line. Hawking handed John Preskill his prize. It was a baseball encyclopedia, a fat reference book stuffed with the records of the sport. Hawking even made a joke about it, saying that from this book, information could be recovered at will, so it was the perfect trophy for a fight about whether information can be recovered from a black hole. The moment became legendary. The world's most famous physicist, publicly admitting defeat and handing over a book about baseball to settle a decades-long argument about the deepest secret of black holes. It was science working the way it should. Follow the evidence, even when it means saying you were wrong in front of everyone. But here's an important note, a trust signal worth stating clearly. Not everyone thought the matter was truly settled in 2004. Hawking had conceded, and his instinct proved right, but the full, detailed proof was still years away. Kip Thorne, his partner in the bet, actually refused to concede at the time, unconvinced the case was closed. And Preskill himself accepted the encyclopedia only a little sheepishly, feeling the deepest explanation was still missing. They were right to be cautious, because the strongest evidence, the island calculations, and the summed-up wormholes that truly bent the page curve, didn't arrive until around 2019, 15 years after Hawking stood up in Ireland. Only then did the math show, cleanly, that the memory survives. Hawking followed his gut early. The rigorous proof caught up much later. So, the bet was paid, the concession was made, and eventually the deeper math confirmed the instinct behind it. Information escapes a black hole. The universe keeps its memory. The sacred promise of quantum mechanics holds, even against the hungriest objects in the sky. You might think that's the end of the story. The paradox solved, the bet paid, everyone goes home happy. But physics is rarely that tidy, because even with the bet settled and the page curve bent, a stubborn splinter of the mystery refuses to come out. We can prove the information escapes. We still can't quite say how. Here's the strange place where we actually stand today. After 50 years of brilliant minds attacking this problem, we can prove the information escapes a black hole. We genuinely cannot say exactly how. Both of those are true at the same time, and living with that gap is deeply uncomfortable. Let's be clear about what got solved, because it's a real victory. The island calculations, the bending page curve, the summed-up wormholes, all of it points the same way with hard math. The memory of everything a black hole eats does come back out in the glow. Quantum mechanics keeps its promise. On that, the case is as close to closed as physics gets. The universe does not forget. But now look at the splinter that still festers. Imagine you could catch every single particle of Hawking radiation from a black hole that swallowed a specific book. In principle, the full memory of that book is there, coded in the glow. The proofs guarantee it. Now try to actually read it. Try to point to exactly how the words of that book got stamped onto those escaping particles, step by step, from inside the trap to the light outside. Nobody can do that yet. The proofs tell us the information is in there. They don't hand us the decoder. They show that the books must balance without showing us every entry in the ledger. Think about a sealed magic box where a coin goes in one slot and comes out another. You have absolute proof the coin travels through. You can even prove no other path is possible. But the inside of the box stays dark, and you never see the coin actually make the trip. That's where physics sits with black holes, ironclad proof of the escape, and a dark box in the middle where the how is still hidden. Why does this stubborn gap survive? Because to fully explain the how, you'd need the thing physicists have chased for 100 years and never caught. A complete theory that fuses gravity and the quantum world into one. Remember, the whole paradox was born from those two great theories screaming different answers. We've learned they can be reconciled, that information survives. But writing down the single, unified rulebook that governs the deep inside of a black hole is still the great unfinished job of physics. And there are pieces still actively argued over. How real are those wormholes in the math exactly? What do the islands truly mean about space and connection? Does complementarity, the two contradictory stories, still hold? Or does the new picture replace it? These aren't settled bar chats, they're live battles at the frontier, with brilliant people on different sides right now. So, the black hole leaves us in a humbling spot. It handed us some of the deepest clues we have about how reality is built: surfaces that store worlds, space woven from entanglement, tunnels linking the far apart. And still, it holds one card face down, refusing to fully show how the memory climbs out of the dark. That missing piece isn't a failure. It's an invitation. It's the exact spot where the next great leap in physics is hiding, waiting for someone to find it. And chasing it has already handed us something priceless, a brand new suspicion about what everything, at the deepest level, is truly made of. Step back and look at the whole journey, because it ends somewhere no one expected. We chased a book into a black hole, terrified the universe had forgotten it. And in fighting to prove the memory survives, physicists stumbled onto a clue about the deepest nature of reality itself. It might all come down to information. Watch how the story kept pointing the same way. We asked where a black hole stores its memory, and the answer was its surface, measured in tiny units of information. We asked how a whole universe with gravity could hide on a flat boundary, and the answer was a hologram, a projection of information on an edge. We asked what space itself is woven from, and the answer was entanglement, threads of quantum information stitching reality together. Again and again, when we dug to the bottom, we found information waiting there. This is nudging physicists toward one of the most radical ideas in science. Maybe information isn't something reality contains. Maybe information is what reality is made of. Down beneath the particles, beneath the energy, beneath space and time themselves, the most basic thing might be pure information, and everything else is the pattern it forms. Flip your whole picture of the world for a second. You probably think of the universe as stuff first. Matter, energy, solid things, with information as just a description we lay on top, like labels on boxes. This radical idea turns that upside down. It says the information comes first. The stuff, the matter, the space, all of it is what the information looks like when it's arranged into patterns. Reality is the message, not the paper. Think of a video game world. It looks full of solid mountains, running water, characters with weight and depth. But underneath, all of it is code, pure information, ones and zeros arranged just so. The mountains are information. The water is information. Pull back the picture, and there's nothing but data, organized into a world. Some physicists now wonder if our universe is like that at the deepest level, not built of tiny bits of stuff, but of tiny bits of information, arranged into the grand pattern we call reality. And notice where this leaves the black hole. The monster that started our whole nightmare, the thing that seemed to erase the universe's memory, turned out to be the greatest teacher we ever had about information. By threatening to destroy the record, it forced us to ask where memory really lives, and the hunt for that answer cracked open the deepest secrets of space, gravity, and reality. The villain of the story handed us the map to the treasure. That's the strange gift of the black hole information paradox. A puzzle that began with pure dread, the fear of a forgetful universe, ended by whispering that reality might be woven from memory itself. The most frightening object in the sky turned out to be a doorway into the true nature of everything. We still don't have the final answer. The complete rulebook, the one that fuses gravity and the quantum and tells us exactly how the memory escapes, is still out there, waiting. But we know where to look now. We know the questions to ask. And we know that the universe, even at its most terrifying, does not forget. So the next time you look up at the night sky and think of those dark, silent traps scattered through space, remember what they really are. Not just destroyers, the keepers of the deepest secret we know, and the promise, written into the very fabric of reality, that nothing is ever truly lost.